had speed, we had acceleration. If I have a car, my speed, my acceleration is coming from my engine, right? That's making it move, right? If I have this little car on this, and I do this, something just made it move. What made it move? So we're gonna start talking about all the things. What's making stuff move? How does it move? And where can we predict that maybe something would go? Oh, let's see if it'll click. I just have clicking problems. Okay, there we go. Okay, so forces, you guys learned this, forces are just a push or pull on an object. Who loves to play tug of war? Who has ever played tug of war? Play tug of war. You know, parents versus kids. Great. And that, so forces, anytime is a force, so anything that is a push or a pull on an object is a force. You could say that breathing is a force, right? You are moving air. You are pushing air away, or you're pulling it into your lungs. So we are enacting forces all of the time here, okay? Forces are measured in something called newtons. You know, Isaac Newton, you know, is nice. So it's good, as we learn about forces, we've got Newton's laws of motion. We can remember that force is measured in newtons, okay? When we're looking at force, everything that we've learned has to have a unit, right? Because if I just say six elephants, right? 6 M&Ms, you know, 6 miles an hour, it matters. So our units always matter. So when we're looking at force, we have this unit of newtons, and it comes in kilograms per meters per second, okay? The reason it's this is because force is mass times acceleration. So we're kind of learning it on the back end, but if my acceleration is like a speed, sorry, that should be squared. So I have acceleration, and we just learned that acceleration is meters per second squared. I learned that in the last one. Mass, not weight, but mass is the amount of something in it, and the base unit for that is grams or kilograms. So if my mass is measured in kilograms, my acceleration is measured in meters per second squared, then it makes sense that force, which we call newtons, has the unit of kilograms per meters per second squared, okay? That's where it comes from. They just initially ask you to kind of memorize it. In that. Okay? And it says it's the force required to make an object with a mass of 1 kilogram move at 1 meter per second squared. Because that means we end up with 1 newton. Right? 1 times 1 times 1. We get all of that. We have a nice 1 in there. So if we have all of these forces, who has ever wanted to be an astronaut? Am I the only one? Good, dang. Awesome. Astronaut, what's the best thing about astronauts? Why would you want to be an astronaut?
Go to space.
Go to space. What is so cool about space?
No
oxygen. Our bodies get full of carbon.
No gravity.
No gravity. Okay, no gravity is great. There you go. No breathing. All right, there's no gravity. So everyone's like, man, you go to space, you get to float in space. You know, an interesting thing is that there are a lot of forces that help keep us functioning. You know, oxygen is helpful as our lungs pull it in. So if you're in space, this is why it's important for astronauts to wear a space suit when they get out, because if not, your body will literally pull apart because there's nothing keeping it together. So we have Earth, we have forces that are enacted on Earth, and there's different things like space that we can look at and go, hey, there's some differences there. So what are the forces at play? What are the things that keep things in motion, keep my table from floating up to the ceiling, you know, or make things move? So it says, initially what we think about is friction. So if I were to roll a ball across the floor, or if I'm going to roll this little car across the table, oh, he fell off. Okay, he slowed down. right? So why was he going one speed in the first place and then stopping in another place? Friction, okay? So you had this cool little picture in your book, and it showed like the up close of something, think like a box and a table. I like to think of it like Velcro. Friction's like Velcro, okay? Everything has a surface on it. Some surfaces are smoother than others. We can make surfaces smoother by smoothing them down, sanding them, putting maybe a polyurethane or something on it. If you've ever done a derby car race, there are different things that you can like smooth it down so that you don't have air friction. You want it to be nice and smooth and glossy, and you're going to paint it nice and slick. Because when you have Velcro, there's different types of Velcro you can get. You can get the real thick industrial Velcro, and it's got real big hooks on one side and a whole lot of fuzz on the other side. And you can hang pictures with that Velcro. Or you can have like the real thin, like little Velcro dots, and you just have a little bit of fuzz on one side and real tiny hooks on the other side, and then those aren't going to hook as well. So friction is that hooking between any two surfaces, okay? Every surface has some sort of tooth. Carpet is going to have a bigger tooth than this table, right? So if I'm rolling the same object on the carpet than I am on the table, the bigger teeth that are the bigger undulations for this carpet is going to slow it down more than the table is. Does that make sense? So as we have friction happens all the time with lots of different things. Friction occurs, we often think of like, you rub your hands together and it's hot. That's because of friction. We're releasing energy in the form of heat. It's kind of like that chemistry thing that we were talking about. So every surface is not completely smooth. Everything that we do has friction, whether it's breathing, walking, swimming, moving our arms, getting dressed, like everything has friction with it. And so it says the roughness affects how closely they can get to one another. So again, if I've got like big, huge undulations, it's going to catch a lot more. We're going to have more friction that way. And so then that keeps things from moving, right? So initially, then the question is, if it keeps things from moving, do objects want to keep moving? Yeah. So we can always ask our question, well, if friction keeps things from moving, so if friction didn't exist, would things keep moving? Yeah, they would. They would keep moving, and that's what we're going to talk about with Newton's laws. So with friction, there's 4 different types. There is static. If we think about static electricity, when you take clothes out of the dryer, does what? Sticks your socks to the sleeve of your shirt, right? So static means still, means non-moving. Static in any situation just means not moving. So static friction means I'm not moving and I want to stay not moving. So when we're looking at friction and we start looking at forces, to overcome the static part means we actually have to get started somewhere. So static friction keeps things that are not moving, not moving. It's going to keep you still. Kinetic, we've talked about the root word of kinetic before. So like kinesiology, the study of motion. Kinetics, if you have Lego, like Technics and stuff, they'll usually use this Nix part of it because it's kinetic, it's motion for it. So kinetic means motion. So if I stand up and then I start walking, I've actually had 2 things that have been in play. First, I was static. Now I am moving. So we have static friction and then we have kinetic friction. So anything that's already moving is going to be in kinetic friction. Let's look at rolling friction. So I had the little cars. What's great about this, if I was going to turn my car on its side and slide it or roll it, which one went further? The black one, the rolling one, okay? Because, let's look at what's really happening. Okay, this is why we have dollies, except for great. If I have a box and I am sliding it across the floor, the entire surface here is in contact with the table or the floor there, and so I'm having to overcome every single point where it is connected. I'm having to break all of those bonds for this box to start moving or to be in motion. However, if we take our box and we have it on wheels, instead of an entire surface, now I just have these little bitty sections of surface to break. So this is why wheels are so valuable for moving, because we don't have as much friction when we're dealing with rolling friction, because we're not looking at the entire surface. We only have friction dealing with that part where just where that wheel is touching the ground. So it's significantly less than the whole amount that's on there. So just like with the car, we have this whole part of the car with his little wheels up here. So he's touching, every single part of him that's touching is getting gripped, versus when our little car is upside down, the only sections experiencing gripping are just the part where the wheels are touching, okay? So then we have fluid friction. Fluid is between anything that is a liquid. So you can think about it like with cake batter, swimming. Do we have any swimmers? I'll have Barrett in here. No swimmers in here, okay? So fluid friction, stuff that's in water, something that's liquid. It's also for a gas. So gases are also considered fluid, because fluid doesn't mean water, right? Fluid just means ability to move. So we have two states of matter that have ability to move. Gas has the ability to move around, and liquids also have the ability to move around. So when something is fluid, it can be both a gas and be fluid, or it can be a liquid and it can be fluid, okay? Air resistance is a big friction issue that we have here on Earth, okay? Let's see. Okay, so another force. So we know that we've got friction forces at work. We're kind of breaking down our different forces here. We've got friction forces, and then we've got gravity. Gravity is super convenient. It keeps us planted on the ground, right? If we were in space, we would not have gravity. We would float all over the place. Our stuff would be everywhere. We would need it contained. Our bodies would pull apart because they wouldn't be contained with something. So gravity, it says, is the force of attraction between any two masses, any two bodies, and any two particles. What's interesting is that everything that has mass has gravity to it. So this bottle by itself has a force of gravity for itself. It is pulling on something. Okay? So the marker has gravity. Everything has gravity. So the bigger the bodies are, the more mass that it has, and the more gravity it has. So each planet has different gravity because it depends on their mass that they have. There's some planets that are gaseous, so even though they're huge, they don't have a ton of mass, so they've got some less gravity to it. You have planets that are bigger or have a lot more mass to them. They've got a bigger gravity than the Earth does. All right? So gravity is actually an acceleration. We don't usually think about it like that. We usually just think of gravity as it just keeps us on the ground. But the reason it keeps us on the ground is because it's actually pulling us down to the ground. It is constant acceleration. I'm constantly being pulled down to the ground at a certain rate. There are two different rates for gravity. One is in feet and one is in meters. So if you live in America and don't want to deal with the metric system, we've got feet per second. If you're anywhere else in the world, they're going to use a metric system for meters per second squared. Okay? So and again, let's look at it. It is an acceleration. We know that acceleration, when we learned acceleration last week, acceleration is mass, or is meters over second squared. So it is a distance divided by a time squared. So that means our unit for gravity must be an acceleration unit. So if you're like, and when they say, well, acceleration is, or gravity is constant acceleration, we have that proof. It has an acceleration unit, so it must be acceleration, okay? So those things are tied together, okay? So it is pulling us down. If we jumped out of a plane, you would be free falling, okay? So you're just at the mercy of gravity. So free fall, it says, is when it's solely under the influence of gravity. So we have two different things. If I drop this marker, it's in free fall. It's acting only with gravity. If I throw the marker on the ground, that is not free fall. We now have two forces working with it. So think about it. Free fall means you just let it go free and let gravity take over for it. Okay? So if we are accelerating, what did we learn about those acceleration graphs? All right? So I've got distance, I've got time, or let's do this, speed for acceleration, and time, right? I have an acceleration graph. What happens as time goes on?
Speed increases.
Speed increases. So if I drop something, as time goes on, the speed is going to increase. So for gravity, I have a constant here. So I've got that's not a straight line. I've got a straight line where my slope is 9.8 meters per second squared, or 32 feet per second squared. But what it's telling me is that as time goes on, my speed is increasing. So if you jump out of a plane, you're going to be going faster 1 minute in than you were 30 seconds in. Yes?
What about terminal velocity?
Terminal velocity is when your air resistance is exactly the same as gravity. And so then you can no longer speed up anymore. So that's terminal velocity. So, but if we think about it, everything is speeding up because we're not looking at constant speed, we're looking at a constant acceleration. But then we can use, what was that term when we're looking at just one point?
Reference point.
No, when we're looking at the speed at just one place. Starts with an I.
Instantaneous speed.
Instantaneous speed. So we can look at it and go, okay, well, at 2 seconds in I was going, this graph also said at 2 seconds in I was going, how fast? Okay, now I'm 10 seconds in, how fast am I going? So we're able to find those instantaneous speeds, and those will be increasing.
I have a question.
Yes, sir.
So, since terminal velocity has to do with air, right? Is it air pressure?
Air resistance.
Air resistance. Does that mean in a vacuum, if you dropped it from a certain height, it could just continually fall and increase speed?
Well, there's no,
So
because there's
it
no
would
air
just-
resistance in a
It
vacuum.
could just increase speed infinitely?
Mm-hmm. Hold on.
Because it's also
Wrong thing.
because then it's going to be moving without time.
Yeah.
Okay. So gravity is helping us come down, all right? And so if gravity is pulling us down, air resistance is pushing back up, or it's going against everything, because we always have equal and opposite reactions. Again, we will address those more with Newton's laws, even more specifically. So as something is falling down, you have the air that's having to move out of the way, because air is made up of molecules, right? So this is an interesting thing to think about. Will you fall faster, or will you have a different air resistance at a higher altitude than at a lower altitude? Yes, because at a lower altitude, your air is denser. Okay, it's packed more together. So when you are trying to drop something like a sheet of paper, let's do this card. Hold this card flat. It was flipping and turning. I did not flip and turn it. Something had to flip and turn it. Correct? Everyone see it flipping and turning? Okay. That's because it is having to move these air molecules out of the way to make room for it to fall. Okay? They can't take up the same space at the same time. So if the card is going to be in this space, then those air molecules have to move out of the way. Okay? So if we are at a higher altitude and our air density is not as dense, we don't have to move as many particles out of the way. Correct? So your air resistance is not going to resist that card as much as it would. So if you're in Colorado and you're timing and we drop it at the same time, like there's going to be more, it's going to take longer here in Oklahoma than it is going to take in Colorado for that tip because you don't have as much air resistance with it. That's another thing. If you have anybody, someone in here's dad's a pilot. Okay. Pilots have to know all of that information because planes stay in the air because of density and air resistance. As the air is moving over the wing, it's actually air pushing up against the wing that is keeping that plane in the air. So when you're flying in different weather patterns because of different weather, whether it's dry or wet, changes your density of your air, different altitudes changes it, and so you have to address all of that. Lots of science involved in that. Okay, so terminal velocity, we already talked about that. Acceleration due to gravity. We have a formula. We all had distance equals rate times time, right? So we have our rate is our acceleration, and our time, we're going to look at this. For gravity, the distance is going to be 1/2 acceleration times time squared. Okay, so where does this come from? Let's see if we can see where it's coming from. In my Algebra 2 class, I teach about different points and finding area between them, and because it basically you're making a triangle, and a triangle is 1/2 base times height. Okay, it falls off of that same exact thing, which is why we have the 1/2. But then let's look at it. We have acceleration, so we have to put a 1/2 in there. What would be the unit for acceleration? What do we know acceleration is from last week? Meters per second squared. Okay. I am looking for a distance, which means I want my answer to be in meters. The problem is that I have seconds squared as part of my formula already. So I need to get rid of seconds squared. So the only way that I can get rid of seconds squared is to have a second squared on top. Correct? Have it multiplied times something, because then I can cancel my second squared. We don't typically operate in seconds squared. We typically say it took 5 seconds. So if we start with 5 seconds, how do we make it squared? We're going to square the entire thing. So when we look at our distance equals 1/2 acceleration times time squared, the reason our time must be squared is because we have to have a unit of seconds squared to cancel out our acceleration seconds squared. Do we see why they did that? And they didn't just say, oh, it's rate times time? Okay. Because we're dealing with that acceleration, we have to make our units. So there's always a reason why they put something extra into a formula. Okay, so I've got this little house and this guy over here, right? He's standing on his roof and he drops a rock. It takes 1.1 seconds to drop. How tall is the house? First, we're going to decide, do we want to work in American units or do we want to work in standard, international? Okay. So we can do it in both. So our distance, we know is 1/2. What is the acceleration? What acceleration are we thinking about? He drops a rock. What acceleration is acting? Gravity. Gravity is the only thing. We know that we've got 2 options for gravity. If we choose, we can choose 9.8 meters per second squared. We can also choose 32 feet per second squared, right? I want my answer to be distance. Which of these units gives me distance? Meters. So I'm either going to end up with meters on this one, or I'm going to end up with feet on our bottom one. Okay, I got to get rid of my second squared. It took 1.1 seconds, so I need to square that whole thing. Right? 1.1 seconds. So now, just working it out, I would have second squared, leaves me with 1.1 squared. Would my answer end up being in feet? Correct, and I wanted a distance. Feet makes sense for distance. And this one, my second squared, and this, my second squared would cancel. My answer would end up being in meters. So we would work out our math here, and we would find out how tall the height from which he had dropped it. Okay? Okay, so here's another example. You're standing on a chair and you drop a block. The block drops for 0.75 seconds before it hits the ground. How many feet did the block fall? So since they're asking for feet, we're going to use 32 feet per second squared. Okay, so you're putting in 1/2 times your feet, and then we have to take our time, and we're going to square our time. Okay, get 9 feet for that one. Okay, so projectile motion, let's go over this one. If I'm driving, so this one is actually fun. I'm going to use Luke as an example. We have a zip line, and we also have cornhole. So Luke created zip line cornhole at our house. So we go down the zip line, and you have the cornhole. You're on the little zip line thingy. Okay, and you got to figure out where to drop the beanbag. Should Luke wait until he is on top
No.
to drop the beanbag? Okay. No, because there's a lot more things. If he were to wait until he was right on top of the cornhole to drop the beanbag, the bag would end up over here. Keep moving. Okay? Projectile motion says it's a combination of our forward velocity plus gravity. Okay? So we know, you read about, like, if you're in a car, you have acceleration, and your mom slams on the brakes, and you go, you lurch, right? It's because your body was moving at 70 miles an hour, and is now, wants to keep moving at 70 miles an hour, but the car is no longer moving at 70 miles an hour, so you're being stopped by your seatbelt. So we're going to keep moving forward. So everything that's moving forward wants to stay moving forward. But once it moves forward, then gravity starts taking over. And they work simultaneously. It's not like all of the forward motion happens and then the gravity happens. So what you have is you have a little bit of motion, a little bit of gravity, then a little bit of motion, a little bit of gravity, and you have this all the way down until it hits the ground. So projectile motion is always in an arc. Because at every point, you have some forward motion and some gravity. And here you've got forward motion and gravity. What is another force that is acting on this projectile if it were to be going forward? That would change, what is the other thing that would change the direction or change the shape of this arc?
Resistance.
Air resistance. Thank you, Ben. Because not only do you have it, the velocity of it going forward, but you have determined how fast it's going forward. You have air resistance pushing the opposite direction. So if you throw the beanbag while there's a big gust of wind blowing this way, it's going to fall faster than if you throw the beanbag and you have a bunch that way. We were talking tennis earlier, same thing. If you're hitting into the wind, you're going to have to be using different force. Your ball's going to fall in a different place on the court than if you were hitting with the wind. It might carry it out the back. So you're going to have to adjust your serve. So we're always working in that. You guys are always working in those. Okay, so the law of motion that we're going to study and then we're going to do a quick little lab section on it is Newton's first law of motion. Okay, so it says that an object in motion or at rest will stay at motion or at rest unless it's acted upon by an outside force. And this is referred to as the law of inertia. In your book, you read about that. Inertia is equal to the amount of movement that is capable in an object. So it's its ability or its desire kind of to move. So something that has a lot of mass in it, it's going to take more to move it. It's also going to take more to stop it. All right? And then also, is it all, Ms. Thompson, is it all on the first law today? I think so. Yeah, it's all in the first law. Okay. So as we go through the stuff with our lab, we're going to be looking just at Newton's first law. It means that if you're in your bed and your mom wants you to get up, you're going to stay in your bed until she comes in there and makes you get up, right? It's a good one. So if you're not moving, you want to not move. If you're already moving, it's easier to keep moving. If you're already moving, it's one of the reasons if you're a long distance runner, they say even if you get tired, like when you're running half marathons or marathons, even if you get tired, like just keep running, even if you go slower, because the moment that you stop and start walking, it takes a whole lot more energy to actually get started again, because you were either already in motion at one rate and you're slowing down. So anything that's already in motion wants to keep moving in the direction that it is at that point. So one of the things that we're going to look at in the lab is we talked about acceleration. Can I have constant speed and changing acceleration? We talked about that.
Oh, yes, changing direction.
Yes, both of you, good job, Gavin. Yes, you can have constant speed. I talked about like spinning a ball over the head. You can have constant speed and yet have changing acceleration, because acceleration is related to direction, right? We don't have negative acceleration, we just have acceleration in the opposite direction, so we're not going to look at deceleration. And so one of the things that we're going to look at in our lab with the marble inside of the pan is exploring Newton's first law of motion, where it says at any certain point, when you if we were slow-mowing, we're just capturing, at that point, what are the forces acting on that object? It wants to stay going with that arrow, wherever it looks like, at that exact point, unless something else is acting on it, okay? And if it's at rest, it wants to stay at rest unless you flick it or move it and start it into motion, okay? So we're gonna do 4 groups of 3, and we're gonna bet each section, and then, so basically we're gonna have 2 groups at one table, 2 groups at the other table, and then we're gonna swap. Will you please go ahead and open up your notebook to lab 7.2. We're not doing 7.1. Sorry, that's my husband. He just had a job interview, so that was a pretty big job. You can pray for that. My best friend right now is having her baby's heart ultrasound scan, so I got lots of prayer requests today. Okay, so the first one that it talks about, they were just looking on lab 7.1. We're not going to do that one together. It's just looking at acceleration with gravity being independent. So actually, if we don't have air, these 2 objects would fall at the exact same time. I did it last week with the different, 2 weeks ago maybe with the different balls. When we drop them, they're going to hit the ground at the same time. Gravity is working at the same time. If we were to put them together, then they get to fall. They would fall together. Okay. So acceleration due to gravity is the same regardless of the object's mass. that is falling, okay, you're gonna have the same acceleration of gravity. The thing that changes it that makes us think like, oh, well, gravity wasn't acting as fast on that is because it might have more air resistance. So it's actually the opposite forces that are helping it. Okay, so in your lab, you've got to write a couple of hypotheses. Okay, it talks about, number one, it says, write what will happen when a coin is quickly removed. So this is the situation that we've got set up. Okay, we've got a jar and a card on top of it with a quarter, right? So write what you think will happen when this card is quickly flicked away. So that is going to be a hypothesis that you're going to need. What happens to that quarter when the card is quickly flicked away? What do you think it will do? Where do you think it will go? Okay. Then the next one is when we slowly pull the card, what do you think will happen to the quarter? If you slowly pull the card.
What do you mean by slowly?
It's going to be like slowly pulled. So one is going to be a quick flick. The other one, you're just like pulling the card.
Will the card fall?
We're looking at what will happen to the quarter. You're answering the question, what will happen to the quarter? Okay. The second part of the lab that we will do is going to be related to this pan, the tiny little marble ball. Okay. We're going to start on one edge of the pan, and we're going to roll the ball around flat on the table. What do you think the ball will do? I think it says on there, okay, write your prediction of what the path, and they show you an A, B, or C, will happen to this marble. So will the marble continue to go in the circle? Right? They show it cut out like this. Okay, when the marble comes around, will it keep going in a circle? Will it go straight or will it flick out? What will the marble do? Yay. Okay. So once you have your hypotheses done, let's do the three of you guys in a group. We'll do the three of you guys in a group. Gavin, go with Jonas and Andrew, and then Ben, go with the girls. Okay? And then set up here. So one group at each spot.
I pull it together. Leap up.
We are not doing the eggs. I forgot the eggs. I will tell you what would happen with the eggs, though. We'll talk about it in a minute. Okay? So you can X out the egg part on there. Make sure and write down your lab partners. Okay. For those of you who are over here with the quarters, so these two groups here, you must set your card up even, right with the jar, and then you're gonna flick at the side. Just flick quickly on one side. All right? Yes, sir. The 15. Okay. For these, you're gonna start with your marble on one side, and you're basically just gonna tip it and get it going. And see where it goes. I assume, right? And you can do it a couple times if you'd like. And feel free to repeat it a couple of times if you need.
Hey!